All right. So we're going to spend some time talking about the major classes of biological molecules, so you know what they look like, kind of what they do, and some of the structural features of them. And we talked about carbohydrates last week, so we learned all this stuff about chirality and three-dimensional stereochemistry. And then we learned a little bit about some reactions, the way they put together to make disaccharides and polysaccharides. Today we're going to start learning about a totally different class of molecules, also important to the body, called lipids. And when we think of lipids, we usually think of fats. That's a reasonable way to describe it. They come from fatty acids, but as we'll see, there's quite a few different types of molecules that fit in the lipid category. And the thing that brings them together isn't necessarily fat, but their polarity. So we talked before about polar versus nonpolar molecules. Lipids are the nonpolar molecules of the body. Most everything else that we deal with in the body is polar. So whether it's water, which is what most of your body is made of, or carbohydrates are polar, proteins are polar, all that stuff has a lot of OH and NH, carbonyls and all that stuff. Fats, lipids are the ones that don't have that. So some phrases that we will sometimes use, especially if you go on into some biochemistry, is instead of saying polar and nonpolar, you say hydrophilic and lipophilic. So you might hear these terms in a biochemical context, in a medicinal or pharmacological context. Hydrophilic is the molecules that can, or the substances that can dissolve in water, and lipophilic are the things that dissolve in fat. So they're named that way. They mean the same thing as what we talked about as polar and nonpolar. All the reasons for them are all the same as what we talked about with polar and nonpolar, but those words are often used because the lipids are the areas in the body and the molecules in the body where that nonpolarity it is. So let's talk about some of these different types of molecules and some of the reactions that they do. And the first class of molecules that we're going to look at are the fatty acids. Fatty acids all have a few similarities of the structure. One is that they are acids, which means they're going to have a carboxylic acid functional group. Remember that? That is the carboxylic acid. Please make sure as you're getting ready for this next exam that you've got those functional groups down from the last quiz. I have those, by the way, for you. I'll give it to you in lab. That you have those functional groups down, that you know how to draw line structures and interpret how many hydrogens are on various things, all that kind of stuff, isomers. That's all going to be a big part of the exam on Tuesday. So fatty acids start with the carboxylic acid, and then the other part of the molecule is a long carbon chain that might look like this. And different acids are going to have different lengths, but they're all at least 12 and up to 20 or so. How many did I draw there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So that makes this one, well, here, we'll just go to the 18, 15, 16, 17, 18. So that makes this called stearic acid, or octadecanoic acid. You don't have to know about those names, but that's what they look like. So you've got this carboxylic acid on one side, and then a long carbon chain on the other side. And that makes a fatty acid. Okay, now that long carbon chain is what makes these things nonpolar. We know that carbon-carbon and carbon-hydrogen bonds are nonpolar bonds. So that whole area of the molecule is going to be nonpolar. Because of that nonpolarity, that means that it's going to have all the things that we've already talked about with those molecules. It's going to have dispersion forces. The strength of those forces is going to be dependent on how well two molecules can interact with each other, kind of overlay each other, and attract each other. Again, if you don't remember that stuff, please go review dispersion forces. This particular fatty acid and ones like it is called a saturated fatty acid. What I just drew. A saturated fatty acid is one that has as much hydrogen as possible. So it's saturated with hydrogens. Saturated as a general adjective just means as much as can possibly go into something, like kind of like soaked. And so it's saturated with hydrogen, has as much hydrogen as possible. And what that means then from a structural standpoint is that there are no carbon-carbon double bonds. Because if we put in any double bonds, that would mean fewer hydrogens than are possible.
There be a single bond? Well, yeah, obviously.
It's connected with single bonds, yeah. So that's how you can have the most hydrogen. If you put double bonds in there, carbon still has to have 4 bonds. So if there were any double bonds, there would have to be less hydrogen. So as you might expect then, the ones that do have double bonds in them are called unsaturated, yeah. So let's look at one of those. Count this thing out right. 1, 2, 3, 4, 5, 6. So it's 18 carbons total, just like stearic acid, but with a double bond between the 9th and 10th carbon. This is oleic acid. This is the most prevalent fatty acid in vegetable oils, so olive oil and canola oil, those types of oils. Have a lot of oleic acid in them. This is unsaturated. So unsaturated fatty acids would have less hydrogen. And the consequence of that is they would have double bonds. Specifically carbon-carbon, since carbon-oxygen double bonds are all the fatty acids. All right, so a couple consequences of that. The main one, the most important one, is the geometric or structural consequence, that saturated fatty acids are going to be stretched out in these long, they zigzag, but they ultimately make kind of a straight shape, whereas unsaturated fatty acids curve. So the unsaturation in those bonds, or in the structure, is a double bond, and it's a specific geometry of double bond called a cis double bond, where the hydrogens are on the same side of the bond. And since we know double bonds can't rotate, when you put that double bond in there, it makes this permanent turn in the structure. And if you have multiple double bonds, then you're going to get multiple turns. So there are actually 2 types of unsaturated fatty acids: monounsaturated and polyunsaturated. Mono meaning one and poly meaning many. So a monounsaturated fat has 1 double bond. A polyunsaturated fat has more than 1 double bond. And we could draw these, but I'm going to use a picture from the book here just because they start to get kind of big. As usual, these notes will be posted, so if you don't want to draw these all out, then you can look at the notes in the videos. But this is just coming from your book. So here are some polyunsaturated fatty acids. You can see they have multiple double bonds in them. In this particular depiction, I think just because of space in the book, they're not drawn geometrically quite right. They would actually sort of start curving around on themselves rather than being stretched out like that. But at least you can see where the double bonds are in these polyunsaturated fatty acids. If you've heard of omega-3 fatty acids, you heard that term, it's like a thing that you're supposed to eat. So that refers to fatty acids where the double bond is 3 from the end. Omega is the last letter of the Greek alphabet, and so the omega carbon of the chain is the very last one. The alpha is the first, and the omega is the last. And so an omega-3 fatty acid, these would all be examples of those, have a double bond that starts 3 carbons from the end. So there's the omega, and then you've got 2, 3, and the double bond there. So that makes those omega-3 fatty acids. So just to put that term here. These are polyunsaturated fatty acids that have a double bond. Three carbons from the end. The end being not the carbonyl, so the other end. So here's the carbonyl on one end, there's the other end, and that's the omega end. All right, so that's fatty acids. Any questions about that stuff? Have you heard some of those terms before? All right, so some of the things that we can understand from the structure here are some of the physical attributes. So saturated fats, saturated fatty acids, because they are these long straight chain, their intermolecular forces are much stronger. They can pack together more tightly and have stronger forces. And that means that they're going to have higher melting points. And that's why most saturated fats are solid at room temperature, because it takes more energy to break them apart because of their strong intermolecular forces. That's also true, as we've talked about before, or it also is an effect with the size of the chain. So if we look at, where is it? There. There's a chart in the book. Here it is. So let's see, we don't need all of these, but let's grab what we can here just to look at them. This is from your book. This is page 602, if you're following along. But here are some saturated and unsaturated fatty acids. You don't need to know these names or anything, but take a look at their melting points and their molar masses, how many atoms they have. So this is going from 10, 12, 13, no, 10, 12, 14, 16, 18, and 20 carbons. As you increase in carbons, you can see the melting point going up, 32, 44, 54, 63, 70, 77. All those temperatures are above room temperature. Our room temperature is generally between like 22 and 25 or so. So those fats are all going to be solid at room temperature. Once you have to go, heat them up a bit to get them to melt. So saturated fats are solid at room temperature. If you think about things like cooking, that's your butter, other animal fats like lard or tallow or beef fat. Then you've got things like coconut oil, palm oil, shortening. These are all fats that are made from saturated fats that are solid at room temperature. Yes. The highest melting point one?
Yeah, the
Eicosanoic acid or arachidic acid?
Yeah.
I don't know. You should look it up. I know stearic acid, the 18 one, is a major component of most animal fats. So our own fat, but also beef fat, butter, milk fat, that kind of stuff. That's in there. I don't know. Maybe the other one is in those also. I don't know. You should look it up and see. So if you really want a high melting fats are good for lots of different cooking applications. They're not great for you because they tend to be implicated in cardiovascular diseases because they make those same kind of solidifications in your body. We'll talk a little bit about how that works in a minute, but they are pretty tasty generally. On the other side are the unsaturated fatty acids. You can see here, and their molar masses you can see are in about the same range as these, even in the high end of the range, but the melting points are much, much lower. So all of these would be liquid at room temperature. And that's why vegetable oils and other types of oils are generally liquid at room temperature. These unsaturated fats, because of their curved, kind of kinked over structure, can't pack as tightly and don't have as strong of intermolecular forces, so they need less energy to melt them. So your liquid at room temperature oils are usually those. These will also, not exclusively, but often go rancid more quickly because the double bonds can make them a little bit more reactive and the shape. So they, when we talk about fats going rancid, we're talking about them reacting with water and some other stuff to not be as good anymore and to make some kind of weird flavors. I don't know, has anybody ever had like an old bottle of olive oil that like kind of starts to smell like cardboard, and it'll kind of go bad after a while, especially if it's in the light. All right, so that's structures of fatty acids. And then if we look, I don't think we need to put this one in the notes, but you can see this in a graph form here. So this is the number of carbons on the x-axis, how many carbons are in it, and the melting point here. So if you look at all the melting points of the saturated fatty acids, you can see that as you add carbons, they pretty predictably increase in melting point. And the unsaturated fats are listed here. So all of these on this line are 18 carbon fats, fatty acids. Here's stearic acid, the saturated one. And then you've got a monounsaturated oleic acid, and then the polyunsaturated linoleic acid and linolenic acid, which decrease in melting point from the number of double bonds. So you can see that adding those double bonds decreases the melting point of the fat. Everybody good with that stuff? Okay. All right, so we're not going to get too much into some of these other molecules because I want to get into glycerides, but one of the reasons that you need things like these omega-3 fatty acids, well, this is an omega-6 fatty acid, but these types of polyunsaturated fatty acids that we're told are good for us, they can have anti-inflammatory effects, not the acids themselves, but they're used to produce these types of molecules, which are called prostaglandins. And you can kind of see how the shape might have come from a polyunsaturated fatty acid. If you see it kind of curving around and now it's reacted with this other weird thing, it has these OHs on it. So definitely a different molecule, but those fatty acids, those unsaturated fatty acids are used by your body to produce these things. And these things are really important in a huge range of biological processes. The book has a whole list of them, everything from inflammatory responses to reproductive stuff to what else, like metabolism, blood clotting, kidneys, respiration. So these are really like used in a whole lot of areas in your body, and you need to take in those fatty acids in order so your body can synthesize these prostaglandins. So that's one of the reasons that those particular things are we keep being recommended to eat more and more of them. We don't make those Polyunsaturated fatty acids, well, they're called essential because we need to eat them. Yeah, so here are some molecules used in blood clotting responses. All right, so let's talk about glycerides. Many of the ways that we experience fatty acids is when those fatty acids are actually parts of esters. They're esterified with a molecule called glycerol. So here's what glycerol looks like. It's got 3 carbons. And each carbon has an OH group attached to it. So if we did a line structure for that, it might be something like this. This is glycerol. If you've heard of glycerin, that's the same exact thing. Glycerol is really the correct name of the molecule. Sometimes glycerin is like a product that you can buy, but it's the same thing. So if you've ever encountered this stuff, it's kind of like really sticky and syrupy. You can buy it at drugstores and things like that. It's sometimes used as a laxative. It can be used. It's used in a lot of creams and lotions because it gives it a certain texture. It's good like moisturizer. Yeah.
Just going back on the last, because I was just reviewing.
Yeah.
So are fatty acids lipids?
Yes.
Yeah. Okay,
Yeah.
sorry.
So that's glycerol. Glycerol is can connect with fatty acids to make esters, and those esters are called glycerides, and they connect through a dehydration reaction that looks like this. So, a little bit more room here. So we'll take glycerol and we'll take a fatty acid and put it next to it. These are different colors so we can distinguish them. There's our stearic acid again. What happens is if you take those parts, so you take an H from one molecule and the OH from the other molecule, and you put those together, what do you get? Water, H2O, right. So these molecules come together, and H2O is lost or comes out. Then to maintain all the bonding and the valence stuff, this O needs to connect to this C instead. And so the result of that, put it here. The rest of the molecule isn't changed. But up there now, this is going to be connected to that carbonyl. And the rest of that fatty acid like this. And then H2O is a byproduct of that reaction. So that is called a dehydration reaction because water leaves it. Or sometimes it's called condensation. And that just means losing that water and putting the other things together. And you can see here that what we've formed is that ester functional group. So now instead of a fatty acid, we have a fatty ester that's connected to glycerol. So that molecule connected to the glycerol now is going to be called a monoglyceride. because we've connected one fatty acid there. How many fatty acids do you think we can connect total to the glycerol? That way. 3, yeah, because there's 3 OHs on glycerol. Each one can end up getting a fatty acid connected. So we can have monoglycerides, diglycerides, and triglycerides, depending on how many fatty acids we connect up there. So we can also get diglycerides. Triglycerides being the most important. So most of the fats that we encounter are actually triglycerides. They're not free fatty acids. Take a bottle of vegetable oil, or you take any other kind of like cooking fats or the fat in our body. Those are triglycerides. All of the things that we just talked about with fatty acids also apply to triglycerides. So when we talk about like saturated ones being higher melting and having a more rigid structure, when they having stronger intermolecular forces that leads to a more rigid structure, that's the case with triglycerides also. So when we have animal fats like butter, we don't have as much of the fatty acids, although there are probably some in there. It's mostly the triglycerides, the esters that we're seeing. Okay, so let's look at the reactions, the opposite reaction then, which is called hydrolysis. And this is what we did in lab last week. Oops. Hydrolysis is the opposite of condensation or dehydration. Hydro meaning water, and lysis meaning to break. So we are breaking this apart using water. So these are reacting with water and breaking apart, and they're just doing the exact opposite thing. So let's draw a triglyceride. A triglyceride would have a glycerol backbone like this. Each of those oxygens would be involved in an ester type bond. And then we'd have our fatty acids coming off of them. I'm not going to draw 18 this time just because I'm getting tired of it. It takes up a lot of space, but we'll just assume that that could be however big we want it to be. Those are our fatty acids coming off there that are connected, making the triglyceride. So here's our triglyceride. And you'll see that geometry is not quite right. We're going to do an activity today. Oh, yeah, I think we'll have time today, where we build some of these, and you can see. Whoops, you can see what triglycerides really look like. Right, it's glycerol making an ester with 3 fatty acids. Let's actually make two arrows here. So there's 2 ways that glycerides can be hydrolyzed. One is with acid. So if we have hydronium, water, or any kind of acid and water, that bond ends up breaking, and we're left with the glycerol that we started with, or that we had before in the previous reaction, and then 3 of those fatty acids as they have come off of this. So the exact opposite of what we just did up here earlier. Instead of combining them together to make the glyceride, we're taking the glyceride and breaking it apart to form the fatty acid and the glycerol. That's one way it can be done in acid. The other way it can be done is in base, and this is what we did last week. So we can take sodium hydroxide in water instead. So that's base. And then we're going to form that glycerol again. But instead of forming the fatty acid, because we can't form an acid if we're in basic conditions, we're going to form the carboxylate, which is just the acid without the hydrogen. It's an ionic compound now instead of a covalent compound. And this is the soap that we made last week. So in base, that bond breaks in a similar way, but the end product is not the fatty acid. It's, we might say, the fatty base. We don't really use that term, but it makes sense, fatty base. The sodium salt of the deprotonated fat aldehyde. So this process in making the soap is called saponification. Oops. You don't need to remember that word. This process up here, where we do it in acid, is called acid hydrolysis. There are both types of hydrolysis, and they're both ways of breaking apart glycerides to reform the fatty acids and use them accordingly. So even though when we take in fats, we're mostly taking in triglycerides, our body, mostly in the stomach, is breaking those triglycerides apart into their constituent fatty acids, and then those fatty acids are used for whatever we need to use them for. All right. So questions about that? Notice here that water has to be in both of these here because we've re-added that H2O that we took out up here. So we have to add the water to do that hydrolysis. Okay. Let's look at one more class of compounds. We're not going to draw them, but we can look at the book. This is page 612. And these are what we call the phospholipids, or the phosphoglycerides. So take a look at these molecules and think about how they are similar to the types of things that we just drew. I'll just look at the smallest one here because I can get it big on the screen. So take a look at that molecule. We've got that same glycerol backbone in the middle there, those three C's going down. Two of them are connected to fatty acids through esters again. So that would be a diglyceride. But then the third one, instead of either just being OH, like glycerol, or having a fatty acid esterified in there like a triglyceride, it instead has this phosphate, PO4 is phosphate. So it's got this phosphate connected to it. And so that makes this a phosphoglyceride. This particular one is called phosphatidate. And then you have phosphatidylcholine, or phosphatidylcholine, lecithin, it's also known as. And these types of structures are all really important in biological systems because they are emulsifiers. Does anybody know what an emulsifier is? Not quite. Got something to do with oil. What? It dissolves. Yeah, an emulsifier is a molecule that is part polar and part nonpolar, and therefore can bring polar and nonpolar things together. Soap is an example of that because it's got its polar charged end and its nonpolar tail, and these molecules are like supercharged versions of that. The phosphate part is negatively charged. Some of these even have then ammonium parts that are positively charged. So this is super, super polar, positive and negative charges here. But the other side is totally nonpolar. So if you have a molecule where one side is totally polar and one side is totally nonpolar, then those molecules can help other polar and nonpolar things to be able to be dissolved in each other. And for our bodies, the most important application of that is nonpolar things like fats and triglycerides have to get around our body through our bloodstream, but our bloodstream is water. So we need molecules like this to help us transport all the other nonpolar molecules. If you cook, you may have used some of these types of things. This one in particular, lecithin, you might see that in ingredients sometimes. It actually comes from, soy has it, but it also is an egg yolk. So anytime you put egg yolks in something to like bring it all together, like if you're making like a mayonnaise or something like that, or hollandaise sauce, that's what that's doing. That molecule from the egg yolk is allowing the oil and water to mix and create this new type of sauce. In your body, it looks more like this page here. This is a little crazy, but let's take this image out and so we can zoom in on it and look at it a little bit. So this is what is called a lipoprotein or lipoprotein. It is this kind of conglomerate shell sphere structure made of lipids and proteins. And this is what's going to be going through your bloodstream, delivering lipids all over the place. You've got various things going on here. So here's this kind of shell with all the junk inside. If we break that apart a little bit, all these little blue things are those phospholipids. So those phosphoglycerides, the blue part is the charged part, the positive or negative part that's on top. And then those tails coming in are those long carbon chains that are nonpolar. So when they make these types of spheres, and then the green things are cholesterols, and which we'll look at in a second, and the purple things are proteins. So they make this kind of sphere thing, and then anything inside can be nonpolar because all the nonpolar tails are pointing inside. So things like triglycerides, which you can see in green with the little tails, dark green with little tails, and the cholesterol esters, which are the light green with the tails, these are things that normally would not dissolve in the blood. But these lipoproteins can carry them around and get them where they need to go because the nonpolar part is in the middle and the polar part around the outside can interact with the water and get into the water. Depending on how these are constructed, that's where we get these high versus low density lipoproteins. Have you heard of this at all? Like LDL and HDL, that's what that stands for. High density lipoprotein or low density lipoproteins. They actually have a picture of it in the book here. Here it is. You have to zoom it out a little bit. You don't need to know all the details of what percentage everything is, but basically the lower density that it is, the more fatty acids are around and the less protein. And so these are these lower density ones are what we call the bad ones because they're going to take more of those fats and those glycerides and the cholesterols. And the higher density ones have more protein and less phospholipid and less cholesterol there. All right, so that's your phospholipids at work. And if you want to know more about exactly how all that works, the book kind of goes through it. When you go on and take physiology and that kind of thing, I assume they'll get more into that. Has anybody gotten into this before? Okay, so a few of you, did I get it right? Is that mostly right? Okay. I'm always a little nervous because it's not exactly my area of expertise, but I think that's about right. Okay, and while we're talking about phospholipids, we can also talk about maybe? What happened? All right, we'll just look at the pictures. We can talk about the phospholipid bilayers. So there's our phospholipid again with its hydrophilic head and its lipophilic or hydrophobic tail. The head, remember, is that phosphate part, and the tails are those fatty acid chains. And these can make those lipoproteins that we just talked about. They can also make these things. They can make a bilayer of the two, where the hydrophilic heads are pointing out and those lipid tails are pointing in. And that makes what we call a lipid bilayer or a phospholipid bilayer. And that is what cell membranes are made out of. So that's another important use for lipids in the body, is to make all these cell membranes. So when we talk about drug design, making medicines, trying to figure out how medicines will work, one of the biggest challenges for those is actually how do you get them into the cell? Because most of the body is water, so you gotta like eat this pill. You gotta have it be polar enough to be in your stomach and get dissolved in your bloodstream and start getting distributed. But then when it gets wherever it needs to go, it also has to make it into the cell. In order to make it into the cell, it can't be too polar because it won't make it through that lipid bilayer. So there are some rules of thumb when they're talking about investigating potential candidates for, you know, a drug that targeted a specific cancer protein or something. Its structure has to be like just polar enough where it's going to get into the body and get absorbed, but not so polar that it can't make it into the cell either. And so those kinds of intermolecular force ideas are always present on the minds of people who are designing those kinds of things. You can have, I know some people in that field, and it just seems endlessly frustrating because you can find these molecules that you know will exactly deactivate the protein that you want and like be the perfect thing to cure whatever disease is caused by that, but you can't actually get it to there because the structure just isn't quite right. So they're always looking for like tweaking it chemically, adding little things, taking off little things, changing the functional groups to try to get it into the cell more efficiently. Well, I assume you're, I don't know, but I think that's like your liver and kidneys job, is to like figure out what's okay and what isn't, and then either break it down or extract it. I don't know. One example I can think of is like artificial sweeteners, for instance, are mostly non-digested. They're non-nutritive. So in that case, they pretty much just pass through your body. You can actually detect them coming out. But I don't know the answer to like other things in general, but I assume it has something to do with that. Okay, so those are the basic structures. One more class of molecules that we haven't talked about are the steroids, which are also lipids. Now, I don't know the like medicinal definition or the biological definition of steroids, but chemically, steroids are any molecules that are made from the same basic steroid structure. What? I said steroids are anything that has the structure that I'm about to draw. Oh. Anything that has the same basic structure that looks like this. It's a tetracyclic structure, meaning 4 rings. So you've got 2 6-membered rings connected together like that. Then a third one that's kind of stacked on top like this. And then a fourth one that's a 5-membered ring. Let me redraw that a little bit better. Instead of a 6-membered ring, we've got a 5-membered ring on the end. So you'll see this type of structure come up a lot in biological molecules, and these would all be considered parts of the steroid family. So rather than draw them all, I will show some here. Yeah. So all of these, the fatty acids, glycerides, and steroids are all lipids? These are all lipids, yep. Including some of the ones we didn't talk about, like prostaglandins and things like that too. All right, so these would be non-glyceride lipids. All right, so one important one that is cholesterol, which you can see that steroid backbone there, those 4 rings, or they call it a steroid nucleus in the book. You see those 4 rings, and then they've got this carbon stuff coming off of them. So again, a very non-polar structure with just that little bit of OH on one side. So that's why the cholesterol often gets transported in those shell type things. and is actually a part of those structures as well. We know that these things, that cholesterol can contribute to narrowing of the arteries by these things building up on the outsides, which can lead to high blood pressure or clogged arteries and heart attacks, heart disease, hypertension. Here are some other ones. So these aren't anything to do with that, but you see that same steroid nucleus. These are called bile salts. So these are the molecules that your gallbladder produces to help you digest fats in your small intestine, in the beginning part of your small intestine. If you get your gallbladder removed, you're no longer producing these, and so that's why you often have to avoid a lot of fatty foods because you just can't process them as well. You don't have these types of helper molecules to emulsify your fats. And then there's also hormones like progesterone, testosterone. We talked about those when we talked about ketones, but those are also based on this steroid backbone. And then you've got cortisone, anti-inflammatory. You've got aldosterone, which comes from the adrenal glands, I think. Yeah, the adrenal cortex. And so those are all going to have that same type of structure. So a pretty diverse types of molecules that do lots of different things in your body, but structurally they all share that same similarity, which makes them steroids and makes them lipids. All right, questions about those? Okay, so we've got about 20 minutes till lab starts, 25 minutes. Let's start on this activity, and if we have to finish during lab, we can finish it during lab. So if we could split up into 3 groups. So we need a multiple of 3 groups. So it probably makes more sense in this class to have 6 groups. And then how many model kits do we have? 1, 2, 3. We've got about 12 kits. So each group can take 2 kits, 2 model kits. Hopefully that'll be enough. Here are the instructions. Oh, you know what? I'm going to do a couple more of these. So rearrange yourselves. You've got 6 groups. Don't make you should do it all by yourself. So somebody, or she can join. But we do need a multiple of 3, so we can't just have 5 groups. Well, let's see. We've got 4 times 5, which is 20. So we should have 4 groups of 3 and 2 groups of 2. Or 2 groups of 4. 4 groups of 3, 2 groups of 4. So go. Let me get the rest of these printed out here.